Welcome. This is a recorded session of the Post-Quantum Cryptography Conference of the PKI Consortium, which took place in Kuala Lumpur, Malaysia. This conference is made possible through the support of the PKI Consortium Post-Quantum Cryptography Working Group and our sponsors SSL.com, Entrust, Keyfactor, HID, and Crypto4A. And with exceptional organizational support from SSL.com, Keyfactor, Logius, POS Digicert, Baker Tilly, MSC Trustgate, and Digitoris. Join the discussion. Join the PKI Consortium. Go to pkic.org/join.
Dr. Somrak Petchartee, hopefully I got that right. Dr. Petchartee is going to be talking to us about evaluating the practical capabilities of contemporary quantum processors in breaking AES. This is really interesting because, you know, I've heard a lot over the last couple of days about things that might be impacted by Shores, not too much on Grover. I'm interested to see if we're going to hear a little bit about Grover today. But with that, I'll leave it over to Dr. Somrak. Take it away.
Okay, thank you. Good night, everyone. Oh, sorry. Good afternoon. I promised that I didn't broke the AES, but for my interesting is to explore the complexity of the AES and the computation power of quantum computer. So as the quantum computer advance, it brings the new threat to to today cryptographics. So we must understand the capability of the current quantum processor in order to participate or vulnerables during the before it's become the practical threat. Okay, I explore all the existing potentially quantum processor from around the world, and I focusing on how those platforms could break the advanced encryption standard. Even though the AES is not replaced by any post-quantum algorithm, but it plays the central role of the hybrid and legacy system during the transformation period. So I look into the quantum processor into three angles. One is quantum readiness, cryptographics, and quantum risk assessment. Okay. Also, we look into the quantum property like superposition and entanglement of all processors existing right now. So, okay, next one. Okay, nowadays, you know that we get into the era of noisy intermediate quantum scale. That means the chip is not really enough for computation, and also they have a lot of noise and scale is difficulty. This was my inspiration. Last year, I proposed a new qubit quantum to International Siam Quantum in Thailand. I proposed a topology qubit with a pure spin control by using the material is called conductive polymer pi conjugate. This material have an unpaired electron which we can manipulate and control with electromagnetics. Okay. And also next week, I'm going to present quantum compiler, which are going to deploy or implement into this hardware. This was the basics, fundamental computing process for quantum computer, which different from classical computer. By exploit the superpositions, entanglement, and measurement. It may look difficult in techniques, but not matter than this, okay? But you have some mathematics to explain that how the complexity of the AES can be broke or not. Up to you can see. Okay, let's see the first step for initialization. At this state, for example, if they have n, you see the circle is n. The circle number is represent the number of qubits. So it can exponentially combine quantum state, 2 power n quantum state. And then for the next step, superposition step, it will be explore the solution, potentially solution in parallels. And then the next step, step number two is inference entanglement. This step is to running the circuit. So to make the solution evident, and where is algorithm implement? Algorithm is implement in the inference, but the circuit is designed in the superposition state. Okay, I will look into the detail how the circuit work. You know, the quantum computer, when they measuring the result, is do in statistics. It can be run 1,000 times, 6,000 times. They use probability to summarize the results. Okay. Right now they have two types of quantum computer. One is circuit based. The other one is quantum annealing. So both of them, when you implement some application, you have to use some algorithms to consume the quantum property, even superposition or entanglement. If you miss some of that, for example, superposition can create parallel state. Entanglement can create correlation. If you miss some of that, it will not be the ideally quantum computer. Currently, not all the quantum chip have both property, but still on the claiming of the paper. So now I list all the technologies for existing quantum chip around the world to explore the superposition property and entanglement property. Okay, you see, for example, IBM Google's Rigetti use superconducting qubit, ion trap, like IonQ, Honeywell's use ion trap technology, neutron atoms, and so on. And then if we look into how they manage the superposition state and entanglement one by one, you see, IBM Google use Josephson junction and use microwave power to manage superposition to control entanglement. So let's look at how they can fulfill the entanglement property into the operations, okay? And then next, ion trap from IonQ. They use electromagnetic power and laser to manage superposition and entanglement into the chip. Neutron atoms use optical twister to maintain the electrons excited with high powers, and then use dipole magnetic to interact and create entanglement. Photonic qubit. You may heard about the photonic chip, right? But photonic chip, they use the continuous writing to do the mathematical function. But photonic chip, they also use for the quantum, in the quantum case, photonic chip just use a single photon. With a single photon, use the same circuit of quantum photon chip, it can do the quantum operations. Okay? Okay. And then what they do in the photonic chip, they use a polarization and beam splitter, like BBO material to split an entanglement photon property. And electron spin with the products from Intel's, they use superposition via the quantum dot. And topology qubits from Microsoft, they use superconductor also, but they do the braiding operation to create entanglement. Okay? Why superposition and entanglement of those quantum chip is very important? For example, you see, this one is superconducting quantum qubit with 20 qubit. You see, you can count from left top down Q1, Q3, 4, 5, 6, 7, 8, 9, 10 until 19. This one is we call full to all interconnection. This is what advantage to create entanglement. What happens if some of those quantum chip doesn't connect all together? For example, this one, they have 8 quantum bits, okay? And you see the gray line which show a variable connectivity from Q1. In case of Q1, we want to interact with Q8. Why we need those all connection? Because when they build the quantum circuit, they have to do correlation. They have to do interaction among the bits. Then they can improve the computation power, okay? what they do in case that those technology don't have interconnect among the bit, they use a compiler. One is compiler used to compile the high-level language, right? You drawing the quantum circuit, right? And compile into the low level to control the hardware. But in case that your hardware cannot do some mathematics, you know, in the previous slide, I list all the quantum chip from around the world. Not all of those chips can do mathematical function from the book from 19 something that they invent the mathematical functions. That means you have to do the via transpiler to compensate those mathematical functions by decomposition or by routing or other things. Okay, that it take time for compute and lose time delay also. Okay, everyone agree that the best encoding, the best algorithm that can have chance to break the AES is Gopher algorithm. Okay, but if we look into not just this paper, they have few papers mentioned about asymptotic improvement. That means even though the hardware is improved, you just change the constant. You cannot change the fundamental asymptotic. That means number of operations to be square root n. Okay? And then we look into the constant and wall clock, we call wall clocks. So, but we try to verify that, okay, if it cannot be better from the asymptotic improvement, it becomes faster in real time, okay. But the number of steps still maintain, that's okay. It's okay? Okay, we look into the more technical detail. So, you see the context of from the theory of Gopher theory. The clock wall is represented by the two operations. It's called oracle time, which take to compute the oracle operation, and diffusion. Most of the searching mechanism in quantum coding always have the oracle and diffusion. But in this case, we implement the Gopher. The Gopher have to be merged with the diffusion. Okay? And we say oracle call iteration to find the mark item among the n possible solution. Okay? N possible solution. But diffusion try to evident, make it evident to guess the target, get the key. Okay? The wall clock in physically is approximated by oracle time in the limit. Okay? If we can reduce this oracle time, it will be faster. Okay? But somehow diffusion operation still in mixing with the Gopher algorithm inside. Okay? Okay. We cannot improve by square root n. Okay. But if something can do, in case that if you make the parallel of the Gopher operation like this, theoretically you can decrease the wall clock time by square root n. This have a lot of people. And I do some simulation to prove this one also, that it can reduce the operation time, okay? The number of operations do the same, but you separate the Hamiltonian space into the n number of the processor, okay? And you see the C constant. C constant is your hardware constraint, time or local still maintained, okay? For each of unit, okay? So, ideally, for AES 128, is to have operation about 2 power 128 possible key to search, right? But it require by using Gopher, it's square root. This number is we got 2 power 64, okay? But in case that you build the QPU million unit, I'm not sure that I think we can do in million unit, right? You can reduce the number of wall clock time 10 to power 10. Okay, this was the key point. We keep this key point number 1. Okay. Okay, this was the reference. Yeah. Okay. Okay, and now we look into the commercial quantum processor in under cloud under AWS. Okay, we look into which one have all-to-all connection or higher number of all-to-all connection. Because higher number of all-to-all connection among the qubit, you can create a high number of entanglement. okay, and you can speeding up, okay. You see, IonQ, Quantum have all-to-all. IonQ use single ion chain. Quantum use ion trap, okay, but 100% full connection, okay. You see, IBM, yeah, 2 or 3% estimate that among the qubit chip they have interconnect. That means only few gate you can do like a CNOT gate to do some correlation among the bit, okay. And IBM, Google also